excuse me, get our recording started and we'll get the fun started for tonight. Let's see here, get my share back going. All right. Good evening. Hope you all are well. It's good to see you all. Get my stuff set back up. One more second. Okay, cool. Up on the screen is what we're going to do tonight with our map check. First and foremost, big item tonight, due at 7 o'clock, is The Way of the Warrior. That's due on Canvas by 7 o'clock. Tonight, we're going to cover proportion mean hypothesis testing, where we know the standard deviation of the population. I refer to that as sigma known. Okay, so if you see sigma known, you know what that means. It means we know what the process or the population standard deviation is. So that's what we're going to focus on tonight. Now let's talk beyond tonight. Tomorrow night, this is purely optional. It's what is color coded in the middle of the screen. Got some folks coming in, so that's why I'm looking over here. I'm doing a thing for the YCP Excel series. It's called Leadership Through Crisis. And that's going to be on at 7 o'clock on Zoom. So if you want to tune into that, you can get the info in a number of ways. Number one, you can look through your email for something from YCP activities. Number two, you can just contact me and say, hey, I want to listen in. Or three, you could email Nate Taylor. It's natetaylor10@ycp.edu. I just want to be clear. This is purely optional. It's not a requirement of this class or anything like that. And as usual, I'm not keeping a black book. So if you don't log in, that's your choice. If you do log in, man, it would sure be happy to see you there so that I know that I'm not just talking to this wall in my room. I do think it'll be recorded. I don't know how that's available afterwards. I'm one of three in the series. So if you are interested, but hey, I just didn't want to sit in at that place and time, just let me know and I'll get you the info so you can watch the Zoom at your leisure. Let's move on to Thursday. We're going to cover the last batch of hypothesis tests. And this will be population means, not proportion means. That's an error I have on a slide, but it'll be population means where the sigma or standard deviation is unknown. And that'll be our last batch. Now, let's talk about Pearson for a second. So over the weekend, I assigned 3 Alpha, 3 Bravo, and 3 Charlie on Pearson. All of those are due this Sunday, no later than 11:59 p.m. You may hear all that and go, gee whiz, I'm just getting through The Way of the Warrior. Now I've got all this homework due. Don't sweat the technique. It's 6 problems amongst the 3 homework assignments. Okay. So even if it does take you, it might take you 1 to 2 hours, but it's 6 problems. And I'm not trying to be patronizing or anything like that. If you need help, please get a hold of me. But it's not gobs and gobs of problems. It's a total of 6. And I believe that if you attack those things sooner than later, then you'll get some good repetitions on all these various types and situations of hypothesis testing. Let's go on to tonight's agenda. Tonight, we're going to cover mean hypothesis testing in the scenario in which we have a standard deviation known. So I'm already recording this session. I want to talk briefly about practice packs that are available for you on Canvas. So if you go to your Canvas, what is a practice pack, you may ask? We'll go to our Canvas, and you've got 3 of them, one for each section of hypothesis testing. So for example, last Thursday, we covered proportion hypothesis testing. So that would be this pack right here. And what it looks like is, if I can just get it come up here. No, Stand by. Here we go. Okay, so there's nothing to do with a practice pack. But what it is, it's screenshots of Pearson, just a couple problems that, for example, this practice pack is on proportions. That's why I have all the pizza up here. And so you can look at a proportion type of problem and have all the answers there for you. And you could do multiple things with this. You can kind of use it as a guide. You can use it to do reps on this. You can ignore the right answers and see what you come up with. That's all there for you. Maybe you don't get to this week. That's okay. It's all on your own time, pace, and schedule. But you have one of these for each type of hypothesis testing. You have one of these for proportions. You have one of these for population means, where we know the standard deviation of the population. And you have one for population means, where we don't know the standard deviation of the population. So those are all there within Canvas for you. All right. So we'll get this out of the way. And so here's what we're going to do tonight. I just showed you the practice packs. We're going to go through something called the frame game, which is just 3 quick problems. All we're going to do is frame the null and the alternative. That'll go by pretty quickly. And then we'll get into the meat and potatoes for tonight, which is mean hypothesis testing in the situation where we know standard deviation. Very quickly, well, let me pause here. If there's any questions, big or small, on anything, whether I've talked about it tonight so far, map check, way of the warrior, anything like that. No questions? Everybody ready to go? Get down to it? Okay, super. All right, back where we are in the zoo, whether it's Disneyland or the mall. You go to the mall sometimes and you're like, all I want to do is find the van, sure, help me get the store, help me get there. Well, this top area, population proportion, this is where we were last Thursday. And if you're like, hey, we've seen this slide before, that's the point. This is the map of the mall. This is the map of Disneyland, whatever. So last week we were in population proportion. Tonight, we're going to be here talking about population mean hypothesis testing when we know the standard deviation. And then Thursday, we'll talk about when we don't know the standard deviation, what to do. Again, just like last time, we covered really the same problem, just kind of 4 different ways. We're going to run with that technique again tonight. Again, strength through repetition. All right. And then we'll do the same technique on Thursday. So to drill down into this yellow box without getting overwhelmed, the bottom line is when we have a population mean and we know the standard deviation, we're still going to use the Z distribution. And from there, we can have a 2-tailed or a 1-tailed test. It depends on the narrative. And regardless of what we have 2 ways of doing each problem. Again, so this is to orient you on where we're headed tonight. And then these slides are there for you to continue to refresh on the situations that you might see in the future, and then reflect on your ability to prosecute and handle, address, and work through problems within those situations. All right, so that is that. Let's play a little bit of frame game. All the frame game is meant to be just a warm-up. Okay? So here we got the frame game. This is how we roll. We'll probably do, this will not be the last one that we do, but we will just do 3 quick problems here tonight. All right, first things first, I got to check this. So let's look at the narrative. So we have Marissa and Tori. They work for Slurp, a sports drink company. Each can of Slurp is supposed to contain 20 ounces with a standard deviation of 0.3 ounces. Marissa and Tori head out to pull a sample of Slurp bottles and validate that the slurp production is working as it should. Okay, so Carrie, why don't you give a shot on what you think the null hypothesis would be in this situation?
Um, I don't know.
Okay, that's a fair answer. Travis, what do you think?
Would it be 20 ounces equal to?
Equal to what?
Oh God, wait. I completely forget. Go back. Is it the would it be the mean or whatever? Can't think of it.
Okay, you're in the right ballpark. Anna Grace, what do you think? What goes here?
Oh, sorry, I forgot I wasn't on mute.
It's okay.
Let's see. Maybe 0.3, the standard deviation.
So on this side, we want, first of all, we only want one number in there, and we aren't going to put the standard deviation in there. So we want to choose in terms of a symbol. We want to either choose population mean or population proportion to go in here. So let's see. Delaney, what do you think? What goes in here?
Population proportion.
Okay, so it would actually be the population mean. Okay, because this is more of a mean than a proportion. Okay. I suppose I could write this better and say an average of 20 ounces. But when we have this with a standard deviation, that implies that this is a mean, because we normally don't talk about a standard deviation associated with a proportion, even though there is such a thing. But regardless, okay, so let's suppose that this is, and it is, we don't need to suppose that this is a correct null hypothesis. Then Nick, what would be our alternative hypothesis?
The population mean does not equal 20.
Okay, super. All right, so to reflect, we have the null status quo, that the population mean, we're not going to use that, is equal to 20. And the alternative is that it does not. This 0.3, we're not going to do anything with it yet in terms of these two, but we will work with it later. All right. And this is a situation in which we have a population mean hypothesis test with the standard deviation sigma known. This is the kind of situation we're going to work through tonight. And this symbology here implies that, what type of test is this? Tim, is this a one-tailed or a two-tailed test?
Is it a one tail?
So this is actually a two-tailed test. This type of symbology tells us it's a two-tailed test because it's saying that is either equal to or it's not. And when we say it's not equal to, that means that it could be greater than or less than, either one. So that implies that it's a two-tailed test. Okay. Any questions on this first frame game? Let's go on to another one. And oh, by the way, these get a little trickier as we go on, just a little bit. Okay. According to a recent report, 48% of people have quit working out since the quarantine. Max does not think this is accurate. So, Connor, what do you think the null hypothesis is here?
Would it be greater than or equal to 0.48, the proportion? P-pop equal to greater than or equal to 0.48.
Okay. So, Alexis, what do you think? Alexis, you're on mute. I don't know if you're talking or sending me some Luke Skywalker like.
Sorry, I don't know if you asked the question. My internet kind of went a little offline. So if you asked the question, I'm sorry, I didn't hear it.
That's okay. So, Alexis, complete this null. We're pretty close. How would you finish up this null hypothesis based on this situation?
Um, it's greater. Then it would be less than.
Okay, Lauren, what do you think?
0.48.
It does equal 0.48.
Wait,
Okay.
or is it?
All right. So this is actually it. All right. And the reason is because Max is not making a statement either way. Max is not believing that it's greater than or less than. So Max is the appropriate alternative hypothesis would be that it's not 48. Okay. Max isn't committing to one way or another. In his mind, he might have one, but we don't really have that information here. Now, if Max thinks it is less, well, that would change things. Okay. So let's say Max thinks it is less. That would change this to be the opposite of what Max thinks. Come on, Pen. Which is that. And the alternative would reflect more about what Max thinks. Okay. So Max thinks it is less. He has to reject or fail to reject the null. And so he would have to write that is either equal to or greater than. Okay. All right. We're going to go to the trickiest one of the evening, and then we'll be done with frame game. We'll move on to hypothesis testing. All right. Okay, here we go. This is the trickiest one. That's why I got Run DMC down here, because it's tricky. Gianfranco makes T-shirts over the past year. It has taken an average of 7.5 hours to make a shirt with a standard deviation of 0.5 hours. 3 weeks ago, we hired 4 new workers. Gianfranco now wants to see if his average shirt making time has decreased to 7 hours per shirt. All right. Colin, what do you think the null hypothesis is?
Decrease. So it would be greater than or equal to 7.5 hours.
Okay. And Alexa, what do you think the null would be?
The mean is less than 7.5 hours.
And Matt, why didn't we do anything with this 7?
It's encompassed by saying less than 7.5.
Yeah. And the other thing is we don't address his specific belief in our null and our alternative hypotheses. Okay, so Matt is correct, Colin is correct, Alexa is correct, but these numbers have to be the same. And even more than that, these numbers have to address our status quo. So we can't put the 7 in here as well, because if we used it in one place, then our numbers wouldn't be the same. And if we used it in both places, we wouldn't be addressing the status quo. So for Gianfranco to generate energy around exploring this 7, he first has to reject or disprove the null hypothesis. Okay? Does this make sense? So this is the trickiest one of the night, because I threw this in here to see, and some warriors want to do something with that 7. They want to put it in here somehow. Okay. Maybe we can use that 7 later. But if we start putting it in here, we start injecting bias, and then we have a flawed hypothesis test potentially on our hands. So we got to be very careful about it. The bottom line is we got to figure out what performance measure mean, which we did, and what number corresponds to that performance measure that relates to the status quo. Okay. Again, in order for me to get support of my idea, I first have to reject this idea that the status quo is going on, which is usually contrary to my idea. Okay. So that's it on the frame game for tonight. It's just a little exercise to get us warmed up and get us in the habit of framing hypothesis tests, null and alternative. This is potentially the toughest part of the process. One could say that this is strategic in nature. It's kind of analogous to, if we don't get this right, then we solve the wrong problem. We solve a problem that doesn't need to be solved, kind of thing. So we'll continue to practice this in the next coming days, just this little kind of exercise before we begin with the meat and potatoes. Any questions on what we just did in terms of procedure, discussion, anything like that?
Yeah, I have a question on the last one.
Okay, this one that we're on, Tim?
Yeah. So,
Okay.
why is it greater than or equal to and less than if the question isn't saying less than or greater than or anything like that? It's just saying a direct number.
I mean, this number here?
Well, I mean, for the hypothesis, it's like greater than or equal to 7.5 instead of just equals to.
Well, because he thinks it's decreased. It's really
Okay.
these words right here.
Okay.
And so this is saying it's decreased. So these are the
Okay.
key words right there. Tim, if this has said Gianfranco, I got all this clutter in the way, but let's suppose that I took off this 7 and I changed that has decreased to has changed. Okay, and didn't do a number or anything like that, then this would be not equal to, and this would be equal to.
Okay.
Does that make sense?
Yeah. Thank you.
So, but he specifically believes that it's become less. And so that, what we have in blue, now that I've gummed this up, I wonder if I could go back and get it out. Now my undo is not working, but let's just do this real quick. So if I get rid of that black here, let me just police that up, and I get rid of this. And and this was that, and this is this. So this symbology right here tells us this is a one-tailed test, because Gianfranco is specifically examining if it has decreased, opposed to the other one that we did earlier where it just is or it isn't. Does that make sense?
Yeah, thank you.
Okay. Any other questions on this? All right. With that, let's pull up our main attraction for tonight. Okay. So here we go. This is our hit list for tonight. Again, we're only going to be dealing with population mean situations with sigma known. We have one problem. We're going to do it two ways. That'll be this two tail. And then we're going to alter it a little bit and do it two more ways. Okay. But again, it may seem repetitious, but the point is to establish strength and comfort within that repetition, so that when we see problems all over the place, we have a base of reference to go back to. So here's the situation. You became the manager of Good Burger 1 month ago. And when you were hired, the guy, the owner, or the manager or whoever said, hey, here's the deal. I'm hiring you, but order times are too long. That means from the time the customer steps into line to the time that they get their order, it's too long. It needs to decrease. This is taking entirely too long. And so that's why we're hiring you to figure that out and figure out how to get these times to be less, these average times. And so you're like, I got it, glad to work here. And since being hired, you thought of 5 ways, you observed things, you put 5 things into place that maybe could decrease this time. Now, just to be upfront, it could be 1 method, it could be 10 methods. The 5 methods really doesn't make any kind of, it doesn't matter. Okay. You could have just paid people more in an effort to try to get them to process orders faster. This isn't really a key part of the problem. But what is the key part of the problem is this yellow box, which is 1 month later, after you've been working there for 1 month with these methods in place, have the order times decreased? So time to conduct a hypothesis test to find out. So that's our situation as we head into this. So the first thing we're going to do is we're going to do this under the structure of a population mean with a two-tail kind of test. Let me get my stuff off here real quick. Okay. So again, you are the manager of Good Burger. You want to determine if the mean waiting time, the average waiting time to place an order, has changed from its previous time of 4.5 minutes. From past experience, you can assume that the population of waiting times is normally distributed with a standard deviation of 1.2 minutes. So, Jenna, what do you think the null hypothesis is?
Would you do mu is greater than or equal to 4.5?
Okay, so you're on the right track. We definitely want a 4.5 over here. Notice that we say has changed. So I think that we could skip down and we're going to do what you just described. But in terms of this one, it just says has changed. Okay, but we're definitely on the right track. And so if that's equal to, then we know the alternative is not equal to. So everybody straight on that? We're just going to address this as if it's a two-tailed test. And that's really basically on this wordage right here. in reality, and pretty soon, I think it's more likely and more productive that we would do it as Jenna described as a one-tailed test. Okay, so this is step one, what we've just done. State the null and alternative hypotheses. So we just did that. Okay. Let's move on. Our step two is our level of significance. That's alpha and our sample size. Well, right here, we have our level of significance. It's given to us. And someone asked me in my other section, would you ever have to come up with the level of significance? In terms of this course, no. In terms of life, yes, it's up to you to decide that. But in terms of this course, I'll usually give that to you. It'll be in the narrative. So we need our level of significance and our sample size. So Cameron, what's our sample size here?
Will be 36.
Yep. So we got a sample of 36 orders. So we've got that. So that knocks out step number 2. Okay, cruising right along. Determine our appropriate test statistic and our sampling distribution. Okay, well, let's talk about sampling distribution first. Because we have a population mean, and more specifically, we know this standard deviation. We can assume that the population is normally distributed with a standard deviation of 1.2, so sigma is known. And because of that, we are going to use the Z distribution. Okay? Now, let's talk about our Z statistic or our test statistic, which is what it's asking for here in step number 3. Our test statistic, or in this case, Z stat, it's going to look very familiar, or it should. I think it will. We're going to take X bar minus mu over sigma over the square root of n. Okay? And probably many of you are recognizing this from sampling. And it's really the same formula. We're just calling it a Z statistic because we're going to use it to reject or fail to reject a null hypothesis. But it's kind of like a hyped up Z score. We're just using it for a different purpose. Okay, but it tells us the same sort of things. So that helps us move on with step number 3. Again, the Z distribution is what we're going to use because we know sigma, and this is our formula for our Z statistic dealing with the sample and population means. Okay, number 4. Determine the critical value, rejection, and non-rejection regions. So let's flash back to critical value methods from last week. When we establish a critical value and a rejection and a non-rejection region, what we're doing is we are establishing areas at both tails of the distribution that we're going to call rejection regions. That's what that RR is. So if we have one here and it's a two-tailed test, and we know it's a two-tailed by this symbology, we're going to have one on both tails. All right, so everything lines up. We have this symbology. It either is or it isn't. That means that in theory, our Z statistic could fall over here, it could fall over here, or it could fall in this white space, which is our do not reject region. Now, how we define where this region ends and begins, and same over here, these are called critical values. And they're going to be the same value, just one's going to be positive to the right side of the distribution, and one is going to be left to the left side. The key to unlock what that critical value is this dude right here, alpha. So 0.05, and we know this is a two-tailed test. Those are the two pieces of info we need to have. We're going to get out of here real quick. Excuse me. And we're going to go to our Z-hacks for the hype table. And we're going to come down here. It doesn't matter what order we go in. Let's just go to this yellow box first because this skull's kind of scary and see if we really need to be scared. Ice Cube is kind of scary too. So we only use these Z-hacks with hypothesis test involving population proportions. Uh-oh, we don't have a population proportion. So what is number 2? Hypothesis test involving population means and standard deviation where sigma is known. We know sigma, so we're in the house. We can use these tables. Super. Do we have a one or two-tailed test? We have a two-tailed test. We know alpha is 0.05. So we go down here and our critical value is going to be plus or minus 1.96. Okay. So with that in mind, 1.96 is our critical value. That's all we got to remember at this point. See you later to ice, to cube. Get back up here. Boom, my stuff's back up. And so let's just make ourselves bulletproof. The critical value over here is going to be 1.96. The critical value over here is going to be negative 1.96. Pearson is going to ask you for decision rules, potentially, in the 6 problems that you've got to work. Let's just write that out. So a decision rule is if Z stat, whatever we figure out this to equal, if that's greater than 1.96, we're going to reject the null hypothesis. I'm just putting an R for short. Or if the Z stat is less than negative 1.96, we're going to reject. Okay? So if our Z stat falls out here somewhere or falls out here, we're going to reject. If it falls in here, we're not going to reject the null hypothesis. All right, so that takes us through step 4. Critical value, got them. Rejection regions here, and do not reject region or non-reject region. Okay, cool. Let's get some red back up on the board. Collect the sample data. Well, we got it. Cameron told us that N is 36. We've got alpha 0.05. We've got X bar. We got to realize that sample mean is 5.1. So organize the results, compute the value of the test statistic. We're going to go up here. X bar is 5.1. Mu is 4.5. Sigma is 1.2. N is 36 underneath the square root. Put all that in. My chicken is taking a nap on the other side of the room. But he told me earlier that was all equal to 3. So, Chastity, if this number, the Z stat, is 3, do I reject or fail to reject my null hypothesis?
You reject it.
Okay, that is correct because of this decision rule right there. 3 falls way out here, okay, which is well inside of that rejection region. Now, let's think really hard about context. Jenna, back to you. So if I reject the null hypothesis and you're the manager of Good Burger, you're not the person who, you're the person we hired to address this problem. What is something that you might do now? Do you celebrate? Do you have a big party?
Um, I'm not sure actually.
Okay, that's all right. It's a tough one. So we hired you to get this number to go down. And the first thing that you have to do is to find, I hate to say evidence, but you have to reject the idea that it has not gone down, and you can't, or you have rejected that. But so you've supported the idea that this number has changed. But which direction do we think this number is going, down or up?
So if you rejected that it didn't change, sorry, it's like backwards in my mind.
Yeah. So we've
So your
rejected
time
that it
went up.
stayed the same. Well, yeah, that's kind of where this is leading us. So we rejected that it stayed the same. All right. So that's kind of good news. But our value is way over here. And what that means is that, okay, this red line here was that 4.5. If our value is way out here, means this population mean is probably shifting over to here. And this whole distribution is shifting over here, which means that since we've hired you, it looks like the times are actually increasing than decreasing. So this is a tough one, but I wouldn't be partying just yet. I'd be actually going back to the drawing board and seeing how we can get these to go down. Okay. So it's a tough one to think about context. Let's keep going. Is there any questions on this method and what we did with the critical value method? All right. So let's do the same problem, just using the p-value method. We'll go through this first part relatively fast because if you notice between the p-value and the critical value method, there's a lot of the same steps. First step, state the null and the alternative. So null, mean, 4.5. Alternative, mean is not 4.5. Okay. Alpha hasn't changed. Sample size has not changed. So that's step number 2. Step number 3, we're still rolling with the Z statistic because this hasn't changed. We still know the population standard deviation. And so therefore, we're still rolling with Z stat, which looks like this. X bar minus the mu over standard deviation over the square root of n. Okay, so that takes us through the first 3 steps. Collect the sample data, compute the value of the test statistic. Okay, we have the sample data, we have 0.05, we have 36. Our X bar hasn't changed from 5.1. So this hasn't changed. We have 5.1 minus 4.5 over 1.2 and square root of 36. And that, again, is still 3. Okay, now I'm going to draw this box because all of this is the same. That's all the same as it was with the critical value method. But now we're doing p-value. And you notice down here, it's 5 steps instead of 6. And that's because we don't have to draw the rejection and non-rejection region kind of things. But what we do have to do is compute the p-value. Okay, so we're going to go to compute the p-value for that z-stat of 3, we could do the norm S distribution function in Excel, or we could just go to our handy dandy Z table, which we never leave home without. So if we go to the Z table and we pull out and look for a Z of 3, that would be 0.9987. Okay, but we know, let me write this a little bit cleaner. We need to remember what we're doing. 0.9987. Okay, and we're going to end up doing a 1 minus. Now, what that 1 minus does is it tells us the right tail. Okay, so first things first, if we stuck with the 0.9987, it would tell us that. Okay, the fact that we do the 1 minus tells us that black portion there, the right tail, which is 0.0013. But remember, with a 2 tail, we always have to take that value and multiply by 2. And when we do this, we capture the left tail. Okay, and then this number, 0.0013 times 2 is equal to 0.0026. And that number refers to that tail added with that tail. That is very important. Okay. So it's in terms of between the critical value method and the p-value method, it's the same concept. We have a distribution. We're looking for if the value falls on the outside of those distribution, at what point we would reject the null hypothesis. With one method, we're using a critical value to find out if it falls there. With the p-value method, we're turning our test statistic into a probability, and then we're going to match that probability against the level of significance. Okay, so let's make a little makeshift diagram. We have p-value. We're just going to park that number right here, 0.0026. And we're going to put alpha right here, 0.05. Remember that 0.05 was given to us right there. And we're going to see which is bigger. Well, the alpha is bigger than the p-value. Okay, and we go back here to our little catchphrases. If the p-value is lower than alpha, then we reject the null. That's the way I rephrase that. If the p-value is low, the null must go. I don't really like the way that is, but if the p-value is lower than alpha, which it is, that means we reject that right there, the null. And then if you want the funny one, if the alligator eats the fish, we reject the null. And sure enough, that alligator is going to eat the fish because the fish is bigger than the p-value. And the alligator goes to what's biggest. Either way, we reject the null, which makes sense, particularly because we already did this problem. We just did it with the critical value method. And the bottom line is, regardless of whether we do the problem with a p-value method or a critical value method, if it's the same problem, we should find the same outcome. So if we reject the null for one of them, we should reject the null with the other one. Okay? Questions on any of this method, what we've done up here? Okay, big takeaways. Again, strength through repetition up to this point when we hit this little red line here. What I mean is this is all the same. Am I saying to memorize the formula? No. What I'm saying is get into the pattern. Am I saying to memorize these steps? I'm not saying necessarily to memorize them, but when you see the step, you should feel like you're seeing an old friend. Aha, I know, I've met you before. I know what to do here. I feel very comfortable. Once we get down in the red box, we have some differences. The main thing is once we turn that 3 into that 0.9987, we need to know what that refers to and what it doesn't refer to. And so it might help to draw that drawing. And when we do our 1 minus, we need to understand that that 0.0013 is only literally half the answer. And to get the true answer, we need to multiply it by 2 to get that total p-value that we then would compare against alpha. So this multiplication is unique to the two-tailed test under the p-value method. And really even more specifically than that, that is what defines the two-tail p-value method, the fact that we have to multiply that by 2. Okay, so tried to hit the big call outs there, the common places of error. And again, if as you're working through problems this week, I would really encourage you to, getting a problem wrong on Pearson, I know it's frustrating as heck, but more importantly is it's kind of like, okay, do I have a pattern of error? Do I have a pattern of misunderstanding? Because once you identify that, all we need to do is get you the cure. And it's relatively simple to, quote, heal you kind of thing. But if you don't have a sense of what your pattern of misunderstanding is, it's a lot harder for us to get you well. Anyway, okay, let's move on to some one-tailed tests. Okay, notice here that we've altered this a little bit. So we have the same situation. You're the manager of Good Burger. You now want to determine the mean waiting time to place an order. You want to determine if it has decreased from its previous time of 4.5. Okay, that's the first thing that's changed from the previous problem. Okay, and in this situation, it's not like you did the other hypothesis test and now you're doing this one. We're just pretending like we're starting from Jump Street here. And like Jenna pointed out, we'd probably more realistically start with this approach because that's why we were hired. So there's a little bit of artificiality in the problem. The other thing that's changed is our sample mean is 4.4. But before we get to that, let's start out with framing this. So Alexis, what do you think is our null hypothesis here?
That the mean is greater than or equal to 4.5.
Okay, very good. And Chastity, what would be our alternative?
That the mu is less than 4.5.
All right, outstanding. Okay, very good. So we see that common pattern. The fact that we have an equal sign in the null hypothesis is what makes it the null. The fact that we do not have an equal sign in the alternative hypothesis is indeed what makes it the alternative hypothesis. These numbers are the same. This symbology is the same. So we are good to hook. That's our first step. And moving on to the second, level of significance, 0.05. And our sample size is still 36. So no change there. Appropriate test statistic. Let's first talk about the distribution, Z distribution. And the test statistic we are going to use is the Z stat. You get one, you get the other. All right, this is all familiar territory. Sounds good. Determine the critical value rejection region and non-rejection regions. Okay, here things are going to start to get a little bit different. Where this symbol is located in relationship to this symbol. Okay, so let's look at, let's get a little magnifying glass, and let's really zero in on that alternative hypothesis for a second. So we're hypothesizing, at least with the alternate hypothesis, that the mean is in the left tail. Okay, it's less than 4.5. So if this is 4.5, we're hypothesizing that the mean has moved in that direction, which means we're going to be working in the left tail when we draw our rejection region. And because of this symbology here, this greater than or equal to or less than, we're only going to have one rejection region, hence a one-tailed test. Okay, this is very, very, very important. We're not going to have a rejection over here. We have rejection region here, and the rest is do not reject. Okay, so with our setup, the only other thing we need is a critical value for that. Please don't make the mistake of going, oh, well, it was 1.96 before, so no, the game has changed. And when in doubt, just follow the steps. So we got to remember, in order to determine critical value for the Z distribution, we're about to go to our hack table, but I need to know that value there for alpha, which is 0.05. And of course, my diagram tells me this is a one-tailed test. So I'm going to get down here. I'm going to go to my Z-hack table. All right. I always, am I authorized to be here? Yes, I am, because I know the standard deviation. Okay, cool. I'm not using a two-tailed test. I'm using a one-tailed test. So I'm over here. And my alpha is I didn't mean to do that. That's what I get for wagon stuff over there. So my alpha is 0.05, but I'm only going to have one critical value. It's either going to be positive or it's negative. The value itself would be 1.645. Because I'm in the left tail, which is the negative side, remember, left of the mean, Z-score for the mean is 0. So anything left of that is negative. I'm going to remember negative 1.645. So I'm going to get out of my hack table. I know what my critical value is. Let me pull back up my stuff. Boom. All right. So my decision rule, first of all, this critical value is negative 1.645. And my decision rule is very simple. If my Z-stat, let me see how I can write this kind of in conjunction with my diagram. 1.645. Yeah, I still don't like the way that is. Let me just do it the other way. Okay. Let's do it this way. Okay, so if my Z-stat is less than negative 1.645, I'm going to reject the null hypothesis. Okay, that's my decision rule. And personally, I don't know, I didn't used to be a big fan of decision rules. Now that more that I use them, I kind of like them. Just kind of makes me that much more bulletproof. I can go, yep, yep, yep. I know what I should be looking for. Okay, cool. Time to collect that sample data, organize the results, compute the value of the test statistic. All right. So test statistic. I have some new values now, so I need to be careful. I know my formula has not changed. X bar minus that, over that, over that. Okay, that is my Z stat. All right, let's put in some numbers for this bad boy. Notice that we have a new X bar, 4.4. This hasn't changed, 4.5. Everything else, 1.2, square root of 36. The chicken can communicate with me telepathically and tells me that the Z-score is a negative 0.5. Okay? So Delaney, based on a Z-stat of negative 0.5, do I reject or fail to reject my null hypothesis?
So you would, I'm going to say you would reject.
Okay. So by this decision rule, all right, -5 has to be less than negative 1.645. So I would need a Z stat of like negative 1.7 or negative 1.8 or whatever that's out here. But the problem is negative 0.5 is compared to that negative 1.645, negative 0.5 is like right there. So I would fail to reject
Okay.
because I'm in the do not reject area. Okay.
Yep.
So let's see. So Lauren, what do you think? So if I fail to reject this null hypothesis, what do I do now? I'm the manager of Good Burger. What do I do?
Well, does that mean you're becoming like faster? Than the 4.5?
So if I had rejected, it would mean if I had rejected my null hypothesis, it would mean that I was faster. But because I failed to reject, it means that even though this appears faster at 4.4 compared to 4.5, here we go with some drop in science with defiance. It is not a statistically significant difference. Now, let's focus on that just for 1 second. So I think without this class, I think the common person would say, well, wait a minute, 4.4 is faster than 4.5. But to put this into plain English, it's not that much faster enough to say that it is a distinctly significant difference in the laws of statistics, which it kind of depends on where you're working. But it doesn't pass the hypothesis test. So you can't be fooled by these numbers. And I'm not saying Lauren was. But if we fail to reject the null hypothesis, we're saying that the status quo is still in effect. Now, n triumphs all things. If n was 360 and everything else was changed, we probably would have rejected the null hypothesis. But based on this information, we cannot reject the null, which means even though this 4.4 appears faster than that 4.5, it's not enough to declare victory just yet. Okay? So just let that sink in. And that alone is just as much the reason for conducting hypothesis testing. I think oftentimes we go into this thinking, well, if it's less than 4.5, we should be good. Well, it depends on a little bit more than that. Okay. So the other thing is, in plain English, if we get these results and we're the manager of Good Burger, back to the drawing board. It doesn't mean we abandon the measures that we have implemented. Obviously, something is working. So maybe we just turn up the volume on those. A simple example would be, let's say we increased everybody's pay by $2 an hour. Well, that got some juice. Maybe we say, hey, how about $4 an hour? That's a simple example. We know that's kind of problematic, but maybe just continuing to turn up the volume on that method would be enough to get this down and for us to get that statistically significant difference large enough for us to reject the null hypothesis. Okay, we've got 10 minutes left. We're going to go through the p-value, same problem, and then I'll get whatever questions y'all have about anything. So same problem, same setup. We're just going to rock out the p-value method. First, let's talk about what's the same. A lot of stuff. Null, mu, greater than or equal to 4.5, less than 4.5. I need to be careful about going fast because when I do, I have a bad habit of making mistakes. Alpha 0.05, N 36. That takes us through step number 1 and 2. Appropriate Z statistic and distribution. Z distribution because we know sigma. Z stat because they go hand in hand. Abbott and Costello, Gwyneth Paltrow, and never mind. All right, so that takes us through number 3. Number 4, collect the sample data. We have level of significance. We have N. We have X bar is 4.4. Compute the value of the test statistic. Again, we're doing X bar minus the mu over standard deviation over the square root of N. And again, we have X is 4.4 from over here, minus 4.5, standard deviation of 1.2 over the square root of 36. And all that in a bag of chips equals negative 0.5. All that is familiar territory. All right. So I went through quickly because we did it before a lot slower than that. Now let's slow down and talk about p-value. Okay, so we need to find out first and foremost, what is the corresponding probability to negative 0.5? We can do this one of two ways. We can do the norm S distribution, or we can go to our handy dandy Z table. If we go to our handy dandy Z table, right there, negative 0.5. So if we take negative 0.5, that corresponds to a probability of 0.3085. Okay, and that is our p-value. We're not going to multiply that by anything because it's a one-tailed test. We park that p-value over here. We don't have to do it this way. I always like doing it because it just makes it all neat. And we point that 0.5, the fish, over here. And we see what happens, okay? If the p-value is lower than the level of significance, then we reject the null hypothesis. Well, the p-value is much greater than alpha. Okay, so that wouldn't work. Let's try the other way. If the alligator eats the fish, reject the null. Well, the alligator is not eating the fish. The fish is over here. The alligator is going to eat the p-value. So we do not reject the null. We fail to reject the null, which is the same outcome we found as doing this problem via the critical value method. So again, in context, because we do not reject the null, we do not have sufficient, I hesitate to say evidence, but that's probably the next best thing. We do not have sufficient evidence or reason to believe that the average order time has decreased from 4.5 minutes. And so therefore, as the manager of Good Burger, we have to continue to look for methods that we can implement in order to decrease that order time, or otherwise we may be getting fired. Questions on anything? Any of this stuff? Anything else? Way of the Warrior? What scene this movie is from? Anything at all?
Hi. So for this one, we don't have to subtract the Z square from 1.
No, and that's a good point. So let's look at that. And again, we're dealing with this tail over on the left, okay, because of where that symbol is in relationship to this. So this area here, Chastity, that's in red, that is that 0.05. But this refers to an area much bigger than that, which is kind of like here. So the bottom line is we don't have to do a 1 minus because we're working on the left tail. Okay. But regardless with this, with this method, so, I think Chastity indirectly brings up a good point, which is how do I know when to do a 1 minus or not? And when you're working on the left tail, you shouldn't have to do a 1 minus. There might be an instance when you do, but I can't think of one offhand. If you're working on the right tail, it depends on how you get this value. But if you're working on the left tail, you should not have to do a 1 minus. Does that kind of answer what you were asking? Okay. Other questions, comments, discussion on anything? Okay, so same things as always. I will post this video later this evening. I have cleaned up versions of all this craziness that I will post at some point within the next day or so that you can cross-check your notes. You can cross-check me. It's a lot cleaner. You can, if there were steps or things you missed along the way, you can hopefully find those out by looking at my notes and so on and so forth. All of this goes towards establishing that foundation of the fundamentals. And so you may reflect and go, essentially, we did 2 problems between this week and last. That is true. But I believe that if we understand how to do those problems, then you can build upon those. And when you see new problems, you can go, this looks like this one that we did or this procedure that we did. So as always, I will hang out until we clear this call. If you have questions, you want stuff you want to talk about, I will be here for you. And otherwise, I will either see you tomorrow night or see you on Thursday. Either way, have a great week. Take care.
Professor Shatskin, I had a question.
Okay.
I just wanted to make sure that you received and can open my video that I uploaded for my Way of the Warrior project. I decided to do the video option, and I'm not, I haven't ever uploaded a video to Canvas before, so I just wanted to make sure that you can open it in the format that I uploaded it in.
Okay. Let me